This is a setup for measurement of intermodulation in receivers. The blue unit is a crystal oscillator, very low phase noise. It produces 25 dBm of power, and there is 13 decibels of attenuation between this oscillator and a 3 dB signal combiner that isolates the two oscillators from each other. The other oscillator is this unit, an HP 8657A, supposed to be a low noise signal generator. It is amplified by 6 decibels in this linear amplifier, class A, low noise, and the two signals are combined here. This one is attenuated by 6 decibels plus 3 decibels, and then we get the same level out from both of them, as you can see on the spectrum analyzer. The power level here is about 8 dBm. It looks like there is a lot of intermodulation, but that's because things are on default settings. If I press amplitude and attenuator, manual, and then 30 minus dBm, it looks much better. I'm sending the signal into two receivers. This is a Perseus running at 2 MHz sampling speed, and here is a PCIe 9842 running at 200 MHz sampling speed. If I increase the level by 1 dB here, and I increase this by 1 dB, you can see this one goes into saturation, and this one also. It means that I have adjusted the attenuation for these two receivers to saturate at the same signal level. This is done by this little network here. The two receivers are fed through different size resistors, and that is to make the signal level the same with respect to saturation in the two channels. Here is also a capacitor. That is in order to produce 50 ohms. The reason is that the capacitor is needed is that here are two low pass filters, this one and that one, and together they produce a small mismatch, and I want the impedance at this side to be very precisely 50 ohms, because it has to be in order for the combiner to isolate very well. This is the impedance at the input of the stepped attenuator. And if I toggle the switches, 1 dB, 2 dB, 20 dB, you can see that the impedance stays within 2 or 3 ohms from 50 ohms when I change the attenuation on the stepped attenuator. This is a matchbox. 3 cables, each one 1/8 wavelengths in length, and 4 capacitors, 1 on each connector and 1 on each variable capacitor. The variable capacitors are then separated by 1/8 wavelengths, so one will do the resistive part and the other the imaginary part of the impedance. This is what I can see on the network analyzer, and I turn one of the knobs, and you can see I can get about 2 ohms in the imaginary axis with this one. So I put it back to 50. And the other capacitor has this effect. You can change the resistive part by about 2 ohms. This is enough to compensate for the variations of the different positions on the stepped attenuator. I can put in, let's say, 10 decibels. And you see there is a small shift which I now easily can compensate for to have perfect balance in the 3 dB splitter. To use the matchbox, I have added this thing, which is a directional coupler, 20 dB iron free. What I can see on the spectrum analyzer is like this. And I can tune the knobs on the matchbox, trying to find the minimum. The thing I minimize is the signal from the other generator, which is reflected on the matchbox and on the load, which is the 2 receivers. I also put a directional coupler on the other generator here and look to what comes in this port. Looks like that, and you can see it is not 0 here, there is some signal. I need to tune the matchbox a little bit differently to bring this one down. And actually I should go somewhere in between. And easiest to do that is to make it optimized for the average frequency. So I switch off one generator, this one, and then change the frequency of the other. And look on the other directional coupler. Here. So I set for minimum on this frequency. Now the signal is weak. If I step the frequency, you can see like that. So the signals will be here and here. The level is, as you can see, minus 80 dBm. The signal going in the other direction here, I can just reverse the direction of the directional coupler and switch on the generator on this side. And you can see here amplitude. It is minus 8 dBm. So the signal coming back causing intermodulation in the oscillators is suppressed by about 70 decibels. That should ensure that the intermodulation in the generators is very low. Now here is the linearity screen from the Perseus. I have tuned to the Hewlett-Packard signal generator, which has the noise sideband here, and I can read the level from the S-meter graph like that. It says minus 0.03, and then I can tune to the other signal. This is the crystal oscillator, and then I can read the signal again like this. And it says 0.05 dB. So both signals are very similar in amplitude. and the level is 2 dB below saturation. It reads 7.5 here, but Perseus saturates 1 bit from the top, so it saturates when these show 6. The PCIe 9842 is 2.3 dB below saturation. Looking here what happens when I change the signal level, I attenuate by 40 decibels. And you can see the signal on the intermodulation frequency has disappeared here. But here on the PCIe it is very different. You can see all the high order seemingly intermodulation products, but it's not. This is most probably digital feedback. So this card has a problem that the Perseus does not have. Here is the result of a measurement of the third order intermodulation. It's not really intermodulation, it's the nonlinearities of the A to D converters. Maybe here we have the 3-to-1 slope. This is intermodulation in preamplifiers, and here it reaches the level where digital feedback starts to give a signal that is more or less independent of the input signal. The signal is about 20 dB stronger in the PCIe 9842. The scale is here is 0 on the attenuator, and I'm attenuating 10, 20, 30 up to 70 decibels attenuation, and the intermodulation is still visible, although weak, down at about minus 115 dB below full scale. The red curve here is the PCIe 9842 at 200 MHz. The green is at 50 MHz. And in both cases, Linrad has been running with the FFT at 50 MHz, taking the average in groups of 4 when the sampling is at 200. The black curve is the Perseus. It seems to have a little bit more intermodulation in its preamplifier, but it has a much better A to D converter. Here is the level of the IM3 quote IM3 unquote product from minus 70 to minus 120. Values very low here are to some extent affected by the noise. I have been using narrow filters to get values as far down as this, but not very narrow. So this is typical for intermodulation measurements on A to D converters, I think. When having this setup running, I can do some other games with it. For example, switch off the HP low noise signal generator. It looks like this. Note what happens with the waterfall here. All the spurs disappear and the noise floor is pretty low. On the PCIe 9842, the noise floor also goes down, but not as deep, and you can see a lot of spurs. There are some spurs here and something close to the strong signal. But Here are also some spurs, but not quite as strong. I can do the other way around, switch off this low noise generator. It has some microphonic properties, as you could see when I was touching it. And now on with the HP, which looks like this when it's only that is running. And again, both of them, and off with that. I can use this directional coupler to inject one more signal into the system. This signal is now sent towards the receivers. And if I step it in frequency, you can see like this. So I put it close to the spur, or on top of the spur here, and you can see in the other receiver it's not on top of the spur there. It means these spurs belong to the receivers, or AD converters if you wish, and not to the signal source. I can bring down the level a little bit. Now it is near the same level of the spur in the Perseus, but it's much below the spur in the PCIe, as you can see. If I go up 10 dB, then you can see these two are relatively similar, not quite, maybe 6 dB. Now, this is not of much interest. I just look at it because it was easy looking at it like this. Note that the waterfall up here is of the same. It spans about 2 megahertz, just like the waterfall here. The reason for a degraded noise floor in the PCIe 9842 is that I'm running it at 50 megahertz. When running at 200 megahertz, it is 6 decibels better. So when running at the full speed, these two AD converters are similar in noise performance, but not in spur performance. Since this has a 50 megahertz sampling rate, I can look at the, let's say, do it like this. I want to see a high frequency here and a low frequency here. Now the waterfall covers the full 25 megahertz of bandwidth that we can have when sampling at 50. Many spurs. I click somewhere and you see it's like this. Or if I move this, a typical level of one of these spurs. Sorry. I move it into the filter. It's 95 decibels below the carrier. It's not really very much. But if I lower the level, let's say I go down 10 dB, the spurs go up. And I go down 20 dB, it could go down. And now 40 decibels. As you can see, the pattern changes with the signal level.